All right, welcome. This is the first of two ancillary videos in the equilibrium unit. This one is on Q, reaction quotient, which is our first final topic. And these videos are for if you didn't quite get it from the POGL or if you feel the need to review on your own. That's what this is for. It's got a little bit more information and it does go along with the notes. So use these if you feel you need to. So Q is called the reaction quotient, and it is used to determine the direction that the reaction has to shift in order to reach equilibrium. Q expression is written as the concentration of products raised to their coefficients divided by the concentration of the reactants raised to their coefficients. Notice that it is written the exact same way as K. That is very much on purpose. The difference is, so they're written exactly the same way, but the difference is that K is for the concentrations of the system when it is at equilibrium. So K is very specifically at this particular state when the forward rate of the reaction is equal to the reverse rate of the reaction and concentrations are staying constant. Q, although it is written the exact same way and calculated the exact same way, is for any possible point in a reaction. It could be for the initial point in a reaction. It could be for like sort of past equilibrium, if you push the system beyond equilibrium and you've got, let's say, too many reactants or too many products. So any given point, the reaction is not necessarily at equilibrium. Although we calculate it the same way, that is the distinction. So how is Q used? And this is really the huge point about Q. If Q is less than K, and this is, by the way, what I hoped you got from the POGL, if Q is less than K, then because they are written the same way in terms of the ratio, then that means that your numerator must be too small. Right? If Q is less than K, then your numerator is too small. So we have to make the numerator bigger. Well, what goes in the numerator? Products go in the numerator, right? It's products divided by reactants. So in order to make the products bigger, the forward reaction must occur. So if Q is less than K, your numerator is too small, your denominator is too large, you're going to have your forward reaction occur, you're going to decrease the concentration of your reactants, you're going to increase the concentration of your products in order to get to equilibrium. If Q is greater than K, well, now we have the opposite situation. So now our numerator is too big, right? There's too much stuff in the numerator. So we have to get rid of the stuff that's in the numerator in order to get Q back down, make it smaller so that it's actually equal to K. What's in the numerator? Products are in the numerator. So in order to get less of the numerator and more of the denominator, we have to have the reverse reaction occur. We have to have the reaction go from products to reactants in order to be equal to K in order to get to equilibrium. Notice, by the way, that reactants are always on the left and products are always on the right. I don't care what you're starting with. You can start with products and generate reactants. So reactants are always on the left, products are always on the right. If Q is equal to K, then we are at equilibrium. So this diagram is simply showing that. If Q is less than K, right here, right, Q is under K, we have too little product, right, not enough product. So we have to go to the right, we have to generate more product. And over here, if Q is greater than K, we have too much reactant, not enough product. No, I'm sorry, that's wrong. Too much product. And we have to go in the opposite direction, right? We have to go in the reverse direction to get to equilibrium. Now, how do you do a Q problem versus how do you do a K problem in terms of calculation? Well, in a K problem, equilibrium problem, we've seen this before. You write a reaction, you fill out a nice chart, you plug into the K expression, and you solve because you know you're at equilibrium. In a Q problem, which will contain such code words, by the way, as are we at equilibrium? What direction do we have to go to get to equilibrium? Is this a solution saturated? Will it produce a precipitate? These are, by the way, code words for basically this is a Q problem. It typically won't say calculate Q and compare to K. There are also 3 steps. And the first step is the exact same thing, write a reaction. But instead of using the ice chart, you actually skip the ice chart because we don't know if we're at equilibrium. That's kind of the whole point. You go directly into the expression. So you write the reaction and then you write the expression, and then you plug in, because you're probably going to be given numbers, enough numbers, and you solve for the value of Q, and then this last bit is where you're going to be answering the question. Compare the value of Q to the value of K, and based on what we talked about in the previous slide, think what direction will the reaction have to proceed in order to get to equilibrium. So with that in mind, we have a question like this, which gives us a reaction, and it gives us, notice by the way, starting amounts. It gives us amounts, and it says, how will the concentrations change at equilibrium? So this implies that we are not actually at equilibrium, so we want to treat this as a Q problem. Now we already have the reaction written, so I'm going to go to the expression then. The Q expression for this reaction is the concentration of HI squared over the concentration of H2 to the first times the concentration of I2 to the first. My smartboard's having a moment. Now notice they gave us moles and liters. We do need concentration here, so I'm actually not going to take the mole values and plug them directly in. I am going to convert moles into molarity first and then plug it in. So this is I2 times H2. So in my expression, I'm going to have the concentration of HI, which is 0.02 moles divided by 2 liters. Notice they gave us liters here, and I'm going to square that. I'm going to divide that by the concentration of I2, which is 0.030 moles over 2 liters, times the concentration of H2, which is 0.01 moles over 2 liters. So simply doing that math, plugging that into the expression, I get a Q value of 0.035. This is also a ratio just like K. In this reaction, it told us the K value. It says right here, Kc at 448 degrees Celsius is 51. So K is 51. So Q is substantially less than K, right? 0.035 and 51 is significantly less than 51. So what does that mean about this reaction? Well, if we think about this in terms of the ratio, which I want you to do, Q is less than K, that means that we don't have enough product and we have way too many reactants. So what direction does the reaction have to shift in order to get to equilibrium? Well, we want to get Q equal to K, so we need to make Q larger. Q is products over reactants just like K. So in order to make Q larger, we need to shift right in order to get to equilibrium. So our products are going to go up and our reactants are going to go down in order to do that. So what are our products, what are our reactants? So the question is actually asking, how will the concentrations change at equilibrium? So I can say that the HI will increase at equilibrium, and then the H2 and the I2 will decrease at equilibrium. So that answers that question. The big thing that Q is used for is actually typically not just a standard equilibrium problem, but instead a precipitate problem. So Q is most often seen in terms of KSP questions, and it will often be phrased like this: will a precipitate form? So take this question as code for a QSP calculation. This is the problem telling you that you need to calculate the value of Q and you need to compare it to the value of K. So it's asking about a precipitate. If you consider sort of any generic solid, we'll say MX2 solid, you write the Q expression like this, or the KSP expression like this, right? 2x minus aqueous, right? This is a KSP reaction. You've seen this before. Well, will a precipitate form? What's a precipitate? A precipitate is a solid that is formed from 2 aqueous liquids. So this thing right here is your precipitate. If it's asking will the precipitate form, then the reaction has to shift to the left in order to form the precipitate, because the precipitate is on the left in this reaction. So what you're really looking for is a situation where you would get the shift to the left at equilibrium. If the reaction does shift left at equilibrium, then you know you're going to be forming a precipitate. And that's what these bullet points are saying. If QSP is equal to KSP, then the system is at equilibrium and the solution is saturated. So that means that if it stays exactly as is, you're actually not going to get a precipitate to form. If Q is less than K, that means that we don't have enough product, and the products are aqueous ions. The products are not a precipitate. So if Q is less than K, then we're going to have to generate more product in order to get Q equal to K in order to be at equilibrium, and we're not going to have a precipitate. But if the value for Q is greater than the value for K, that means that you have too many products and not enough reactants in your system. And in order to get to equilibrium, you have to use up some of your products and you have to generate more reactants. Well, that's going to be a shift to the left. And in this case, shifting left creates a precipitate. So the answer would be yes. So standard question, will a precipitate form 1.1 liters of 8 times 10 to the minus third molar lead 2 nitrate is added to 0.4 liters of 5 times 10 to the minus third molar sodium sulfate, and it gives us the KSP of lead 2 sulfate. So again, our equilibrium problem solving process, but adapted for Q, the first step is to write a reaction. What reaction do you write? You write the same reaction that we're used to writing, meaning you write the reaction based on the K value. It gives us the K value of PbSO4. So I'm going to write PbSO4 solid goes to Pb2 plus aqueous plus SO4 2 minus aqueous. And you're going to skip the ice chart, but then you're going to write the QSP expression for this reaction. Pb2 plus times SO4 2 minus. If we plug in our concentrations of lead and sulfate and get a value for Q, we can compare it to the value for K that's been given and determine if we're going to get a precipitate to form. Again, this right here is our precipitate. This is our solid. Now, at this point, you'd probably be tempted to use the molarities that have been given to you in the problem, because after all, it gives you the molarity of lead 2 nitrate, and after all, it gives you the molarity of sodium sulfate. If you did that, you would be wrong, because of course, it has to be a little bit more complicated than that. Notice that we are diluting the concentrations. We are combining volumes. We're combining 0.1 liters with 0.4 liters. So the molarities that we have of the lead 2 nitrate and the sodium sulfate will not be their final molarities, and we actually have to calculate that first before we plug into the Q value. So the lead 2 nitrate, this thing is soluble, completely soluble. It's got nitrate. So this gives us lead and 2 nitrate ions, right? We're concerned with the lead because that is here in our QSP expression. Sodium sulfate is also soluble, so that gives us 2 Na plus ions plus a sulfate ion. We are concerned with the sulfate ion because that is here. So basically these compounds that they've given us are giving us the ions that could possibly form the precipitate. But I need to calculate those molarities first, and there are 2 ways to do it. I'm going to show you. We're going to do both. The first way is using the definition of molarity using moles per liter. So for the lead, we know that it's 8 times 10 to the minus third molar. So I can solve for the number of moles of the lead in the 0.1 liters, and I get 8 times 10 to the minus fourth moles of Pb2 plus. But then I have to take into account that I will have this at the end in a total of 0.1 liters plus 0.4 liter solution, right? So I'm going to then divide in order to get the concentration of lead in the final beaker. I'm going to take my number of moles, divide by the 0.5 liters, and I get a concentration of lead that is 1.6 times 10 to the minus third molar. That's the value that I would then use in my Q expression, because that would be the actual concentration of the lead in the beaker as soon as I combine these 2 things. But if you've been paying attention, you'll notice that we are actually diluting both of these concentrations. So I could also use M1V1 equals M2V2, and that's what I'm going to use for the sulfate. You can use either. So the initial concentration of the sulfate is 5 times 10 to the minus third molar, and I initially had 0.4 liters of it. I'm looking for the new molarity, and I know that the new volume is going to be 0.5 liters. So the new molarity, simply solving for the sulfate, is 4 times 10 to the minus third molar. So this is my sulfate concentration. I have to erase some of that, but those are the values that we're now going to plug into the the Q expression and then compare it to K. So QSP, simply taking those values, is going to be 1.6 times 10 to the minus third times 4 times 10 to the minus third. So I get a QSP value of 6.4 times 10 to the minus 6. The KSP value that was given in the problem is 6.5 times 10 to the minus 7th. Q is greater than K, because 6.4 times 10 to the minus 6 is greater than 6.5 times 10 to the minus 7th. Watch your exponents. Okay, Q is greater than K. So what does that mean? It means that we have too many products, right? It means that we have not enough reactants. So we're going to have to shift left in order to get to equilibrium. When we shift left in this reaction, that's the reaction that we're looking at, we're going to generate more PbSO4 solid. So yes, precipitate forms because of this shift to the left, because the lead ions and the sulfate ions are basically in too high of a concentration. They're going to have to bring their concentrations down. The only way to do that is by reacting in the reverse direction in order to generate PbSO4 solid that will pull the excess Pb2 plus and SO4 2 minus ions out of solution. The last type of problem that is seen with QSP is two precipitates, a question where they'll basically give you information about two separate precipitates and ask which one will form first, or questions to that end. So if we have two precipitates, you want to think about the precipitate that requires less of an ion in order to actually form the precipitate. That's the precipitate that's going to form first. Because when you're adding stuff into a solution, you're always starting at 0 molar. Even if you think about titration, at the beginning of the titration, you haven't added anything into it. So whichever precipitate needs less ion, whatever ion you're kind of adding in order to actually reach the point where it starts precipitating, that's the precipitate that will then form first, the one that needs less of the stuff. And we're looking for, basically, this is our tipping point. When QSP is equal to KSP, then it's perfectly saturated. And as soon as we cross that tipping point, when Q is greater than that value, that's when we're going to start our precipitation. So, example problem, solution contains both silver and lead ions. Concentration of the silver is 1 times 10 to the minus second. Concentration of the lead is 2 times 10 to the minus second. And then it gives us KSP values for silver chloride and lead 2 chloride. And it asks, what is the concentration of chloride ion needed to precipitate each metal ion, and which metal ion will precipitate first? Justify your answer. Well, the first one is actually all the calculations, and the second one is simply analyzing our calculations. Using the same process that we've done so far, you want to start by writing a reaction. Well, which reaction do you want to write? You want to let the K value be your guide. But this problem gave us 2 K values, right? Okay, write 2 reactions. Write 1 reaction for each K value. So for AgCl, it's KSP, so it's going to be AgCl goes to Ag plus Cl minus, and this is the solid. Remember this thing right here, that's the precipitate, the AgCl. And PbCl2 goes to Pb2 plus 2Cl minus. Again, the PbCl2 is the precipitate. It gave us 2 K values, so okay, let's write a K reaction for each of them. That's a great place to start. What do we want to do next? For a Q problem, you want to write the expression. So the QSP expression for this is going to be Ag plus times Cl minus, and this is going to be the concentration of the lead times the concentration of the chloride squared. And we want, it's asking about precipitation, right? So it's asking about precipitation. So the precipitation starts when Q is greater than K. So in essence, we can take the K value, but it's like literally right after when they're equal. So I can take the K value and essentially plug it in kind of like this. If Q is greater than K, then I know that if my concentration of silver times my concentration of chloride is greater than KSP, then I'm going to start precipitation. Likewise, over here, I can take my KSP and, I'm sorry, make that, if it's greater than, if the concentration of lead times the concentration of chloride squared is greater than the value for KSP, then I'm going to start my precipitation. At this point, look at what we have in the problem. It gives us K values for both of these things. It gives us the concentration of the silver ion and it gives us the concentration of the lead ion, and they're in the same beaker, so we don't have to worry about dilution calculations. And it's asking for the concentration of chloride ion needed to precipitate each one, meaning it gave us KSP, it gave us silver, it's asking for chloride. It gave us KSP, it gave us lead, it's asking for chloride. We have everything we need at this point to calculate our answer, to calculate the chloride concentrations, and with that we're actually answering every other part of the problem. So at this point I'm simply going to plug in and solve for chloride. So AgCl, I've got 1.8 times 10 to the minus 10th is equal to, I'm sorry, it's got to be greater than 1 times 10 to the minus 2nd times the chloride concentration, and the chloride concentration has to be greater than 1.8 times 10 to the minus 8th molar in order to start precipitating the AgCl. So that's what that number means. As soon as the chloride concentration becomes larger than 1.8 times 10 to the minus 8th molar, you're going to start precipitating your silver chloride in this. Because you're starting at 0. Basically, it says we don't have any chloride to begin with. We're starting at 0. And as soon as we hit that number, we're going to start precipitating the silver chloride. I'm going to do the same thing for the lead. So I've got 1.7 times 10 to the minus 5th, and the lead concentration is 2 times 10 to the minus 2nd, and we're looking for the chloride concentration, which is squared, so keep that in mind when you're solving. So for this one, as soon as the chloride concentration is greater than 2.9 times 10 to the minus 2nd, we will begin precipitating the lead 2 chloride. That's what that value means. So that right there actually answers the first part of the question. What is the concentration of chloride ion needed to precipitate each metal ion? Boom, there we have it. In order to precipitate silver chloride, you need 1.8 times 10 to the minus 8th. In order to precipitate lead 2 chloride, you need 2.9 times 10 to the minus 2nd molar chloride. So you've answered that question. With that, we can then look at the second one. Which metal ion will precipitate first? Justify your response. Here's where you don't have to do any additional calculations. You've already done them. So looking at these two values right here and comparing them, I can see that the silver chloride needs significantly less concentration of chloride, right? This value right here is less than this value right here. So what does that mean? It means that the silver chloride will precipitate first. Right, this thing will precipitate first because you're going to get to 1.8 times 10 to the minus 8th molar chloride much sooner than you would 2.9 times 10 to the minus 2nd chloride. It's a smaller value. So the answer, you'd simply say AgCl requires less chloride to begin precipitation. Requires a smaller chloride concentration. And that's it. So that's our Q problems in a nutshell.